Alright, and welcome to unit number 4 on conservation of energy. This video is on lesson number 2, kinetic energy, and example problem number 2. Now in this example problem, it gives us a little bit of information about a car. It says this car is 8,000 newtons, so that is the weight of this car. The force of gravity really is what that value is. And it's saying that this value is accelerating from rest to a speed of 15 meters per second along a level surface. So I think I can add on here VI is equal to 0 meters per second, VF is equal to 15 meters per second. Alright, so along a level surface, if the work done by the propulsive force is 110 kilojoules, determine the work done by friction. Okay, so we have this propulsive force is going to be acting forward on this car, doing the acceleration. So I think we can probably put a little line on here and say that the acceleration is going to be in that direction. And our friction is then going to be moving against this. So on here I'll put the work done of the propulsive force as well. I'll say work done by propulsive is equal to 110,000 joules, and we are looking for the work done by the friction force. This one here, question mark. Great. So this is a nice setup. This question, it gives us a new formula to kind of toy with, and really it's saying that the net work done on a system is going to equal the change in its kinetic energy. So up till now, really all we know about work is that we're either adding or removing energy from something. And in terms of adding energy, typically it's going to be either making that object faster or making that object slower. And so kinetic energy is energy related to an object's speed. So let's write that one out, but I'm not going to start with it right away. We have the net work net is equal to the change in kinetic energy. So really this is going to be, change in kinetic energy will be equal to kinetic energy final or after the situation is all done minus what it was at the beginning. So kinetic energy before. Alright. I think largely we see that we might be able to deal with that here because we're going to have a zero energy velocity or a zero energy value here, and then in the final value we'll be able to have actually a rather large energy value. Alright. Before we can do anything with this problem, we need to solve this object's mass. The question was kind of clever and gave us the weight of the object, but we can't do anything unless we have this weight in kilograms. So let's just solve for that weight first down here. So force of gravity is equal to mass times little g, and that's really what this is giving us. So let's say that mass is equal just to force of gravity divided by little g, which in this case is 8,000 divided by 9.81 meters per second squared, which works out to 815.49 kilos. Okay, that's out of the way. That's pretty nice. So here I have us solving for the net work on this system, but the question is not asking for the net work. The question is asking for the energy due, or the work done by friction. Really, that's the total energy that's going to be changing due to friction. And so really what we're going to want is once we find this net work formula, we're going to be doing similar to what we do with forces. I think this will be enough space to solve that. And we'll be doing the net work is equal to the sum of all the work done on this object. Well, the sum of all the work done on the object is the sum of all the forces times their distance on this object. So this will be, the work net will be the work of the propulsive force plus the work of friction. And this is almost identical to the force net is equal to the force propulsive plus the force of friction. Except each of these terms now is just getting multiplied by the distance that this box travels. Alright. This question gives us the propulsive force. If we solve for the net force up here, we will have the net force. And then we can solve for our friction force. And that's ultimately what we want. The work done by friction. Okay. So I'm going to swap back to red and solve this top part, and then we can move down to the bottom. So the net work done on this object is equal to the change in EK, or written out, energy kinetic after. So 1/2 times our mass, which we have down here, 815.49 kilos times velocity squared, so 15 meters per second squared. Okay, we can subtract EK before, but if we take our 1/2 mv squared formula, for this second case, initial velocity was 0, right here. Vi is 0, and so that means v is going to be 0, so this whole term will just equal 0. So I'm just going to get rid of this, not worry about it right now. If we did have an initial velocity, absolutely, we would be subtracting these two values, but we're just subtracting 0. So let's plug this into our calculator, and we get the net work done on this object to be, one sec, I have to punch this into my calculator, 15 squared times 815.49 divided by 2 gives me 91,742.43. Network is, let's just go 91,743. And that is in joules. Alright. So this is doing pretty good here. Let's now move this value down to the bottom in blue. So we have our net work now done on this object. So it's going to be 91,743 joules. Remember, this object's accelerating to the right. Is going to be equal to the work done by the propulsive force. That's given to us in the question. 110,000 joules plus the work done by friction. You can imagine friction is going to be moving opposite to the acceleration. So it should work out to a negative value because it's going to the left. Right? It's reducing the amount of energy in here. So when we rearrange this, work due to friction should equal 91,743 minus 110,000. So work due to friction in this question works out to, I get 18.3 kilojoules. And so we could also write out, this is in 3 sig digs by the way, but you could also do 1.83 times, would that be 10 to the 4? I better write that out. 18.3, 2, so 1, 2, 3, 4, correct. 1.83 times 10 to the 4 joules. Either of these two answers is going to be correct, and I'll just toss a box around these, and we'll call this video done.